Okay, hello everyone. We will now be discussing the hyperbola. This will be the last conic section that we will be discussing. Now, the only difference between the definition of a hyperbola and the definition of an ellipse is that for an ellipse, you remember the distance from a certain point in the ellipse to the two foci. If you sum them up, then it will be constant for every point on the ellipse. So every point you choose on the ellipse, right? Now for the hyperbola, this is not the case. So they actually differ in that the distances from the foci to a certain point on a hyperbola has a constant difference. Let's say, for example, we have here distance d1 and distance d2. Okay, so d1 minus d2 will always be constant. Okay, so this is constant. So we're using the absolute value here because we also have another curve right here, and it could be negative. But the distance, so distance is a magnitude, so it is a scalar value, so we need to take the absolute value for that. So so that is the definition of a hyperbola. Okay. So now let us study the different parts of the hyperbola. So we have here, two foci first, and the center, and the hyperbola has two axes of symmetry. So it has a transverse axis, as you can see here, and also a conjugate axis. Okay, the transverse axis is where the endpoints of the transverse axis are the vertices, as you can see here, and the endpoints of the conjugate axis are the co-vertices, as you can see there. Okay, and there are also asymptotes. Okay, asymptotes are lines that our curve will never touch. Okay, they approach them but they never touch. So these two asymptotes right here. So we can arrive at a formula for these asymptotes. So those are basically the parts of the hyperbola. Now let's move on to showing the standard form of the hyperbola. Okay, so as you can see here, let's first write our a here, which is the distance from the center to one vertex. Okay, so this is more or less the same notation in the other conic sections. And also, as you can see here, this is our c is the distance from our center to focus. Okay, so it's the same here on the other side. And as you can see here, we have b right here is not on the curve. B right here is not on the curve, and you will see b actually in the derivation of the standard form of the hyperbola, and it is in the module. So if you are curious about that, how the standard form of the parabola is derived, you can look at the module. It is very detailed there, step by step. So we cannot cover it in this video because it is quite long. Okay, and now you have here the formula of the asymptotes. Y is equal to negative b over ax, and y is equal to b over ax. Okay, so the relationship between a, b, and c here is that b squared, so b squared is equal to c squared minus a squared. Okay, so this is different from the relationship of these three variables in the ellipse. So in the ellipse, the relationship was a squared is equal to b squared plus c squared. So let's not get confused with these relationships. So they are different for the case of the hyperbola. Okay, so we will be using these formulas later for finding the formula. The standard form of the hyperbola. Okay, and the same with the ellipse. The standard form can also vary depending on the location of the transverse axis. As you can see here on the illustration on the left, the transverse axis is on the x-axis, right? So if that's the case, our standard form is x squared over a squared minus y squared over b squared is equal to 1. Okay? So it kind of looks like the formula for the ellipse, but as you can see here, this is minus and not plus. So if the transverse axis, on the other hand, as you can see here on the right, is on the y-axis, our standard form will change to x squared over, y squared over a squared minus x squared over b squared is equal to 1. Okay, so let's take note of these two equations as we go through the examples. Okay, so let's start doing the examples, and I will see you in the next videos.